Hi, my name is Oktay. Today's video will be about water. It will be about its unique properties and statistics about water and about water on other worlds. And here you can see the model of the 3D model of the molecule water, H2O. You have two representations of this model. You have the space filling model and the ball and stick model. Water has a band structure with an angle of 104.5 degrees, and it has a dipole moment. Means it has a one side, that's the oxygen side, which has a negative partial charge, and a side with a positive partial charge, that's the hydrogen side. And the absolutely correct model is the space filling model, because when atoms make atomic bonds, they always have a partial overlap, and that's why this model is absolutely correct. But the ball and stick model is also useful. It can give you an idea of a position of a functional group within a molecule. That's why both these models are useful. This is one of the fundamentals of chemistry. First, ionization energy. It explains why water has the formula H2O. You can see in each period there's a maximum where the noble gases. First ionization energy is the energy that you need for taking away the one outer electron from this atom. And you can see the noble gases have a maximum, and the alkali metals are at a minimum. So obviously noble gases have a complete shell of electrons. Obviously this configuration is very stable, and this explains why other chemical elements like to make bonds, like atomic bond, ionic bond, metallic bond, and the complex bond. And in this diagram, oxygen is 2 positions to the left of neon. And oxygen likes to make 2 bonds, and by making 2 bonds, it gets the same electron configuration as neon. And hydrogen is to the left of helium, and by making 1 bond, it gets the electron configuration of helium. That's why H2O. This is a diagram of the abundance of the chemical elements in Earth's crust, and you can see a tendency. In general, elements with an even atomic number are more abundant, but there are exceptions. For example, hydrogen, lithium also quite abundant, chlorine, fluorine, and nitrogen also. But this scale is a logarithmic scale, and in the rock forming elements are oxygen, silicon, potassium, calcium, iron, aluminium. And this explains why there is so much water in the universe, but also on Earth. And the elements with the even atomic number are more abundant because in the universe the second most abundant element is helium. It has 2 protons, and helium is the building block of these elements. For example, if you put 3 helium nuclei together, you get carbon, and with 4 you get oxygen, and that's why these elements are so abundant. This is the secret of the molecule H2O, water. It's the intermolecular hydrogen bond. In my first video I have given you an example. That was the molecule DNA, deoxyribonucleic acid, where a high number of these bonds give this DNA molecule its double helix structure. And for this to work, you need polarized hydrogen atoms, and you need 3 electron pairs. Yeah. The bond angle is in water is 104.5 degrees. That's not the bond angle of a regular tetrahedron. It's 109.5 degrees. And the reason for this is water has 2 free electron pairs, and they press the hydrogen oxygen bonds a bit together. That's why you have a bit smaller bond angle. To understand the polarity of bonds, you need this concept of electronegativity. It was developed by Linus Pauling, and it gives you an idea about the strength of an atom to attract electrons. This is a nice diagram. It does not contain all the elements, but it gives you a good idea of the tendencies. There are two trends here. One, you can see the elements in the top right corner are at the top of the scale, with fluorine at the top at 4.0. Oxygen 3.4 is the second. And you can see the elements at the left. The alkali metals are at the bottom of the scale with about 0.7 to 1. And all the other elements are in between. And for example, if you want to compare the hydrogen-oxygen bond with the hydrogen-sulfur bond, you see that here is a big difference in electronegativity. This means you have a highly polarized bond, whereas with hydrogen and sulfur you have a low difference in electronegativity. That's a low polarized bond. And you can see from the second to the third period in the group of the nonmetals, there's a big drop. These are other hydrogen compounds other than water, and you will see that these molecules have some problems with this intermolecular hydrogen bond. For example, methane doesn't have a free electron pair, so it can't make a intermolecular hydrogen bond. And you got hydrogen chloride and hydrogen fluoride. The HF bond is more polar than the oxygen-hydrogen bond, but you have a problem because you have just one hydrogen, polarized hydrogen per molecule, but you have three free electron pairs. And this means that two of the free electron pairs will be unoccupied, and this means that this intermolecular hydrogen bond has a weak effect. A similar problem with ammonia, this NH3. This time you have three polarized hydrogen atoms per molecule, but only one free electron pair. That's not really working, and yeah, that's a weak effect. With hydrogen sulfide, H2S, it seems everything is okay. You have two polarized hydrogen atoms, and two free electron pairs, but the hydrogen sulfur bond has too little polarity, and that means your intermolecular bonds are very weak. And that's why all these compounds are gases, and this effect is weak with these molecules. But with water, it's a different story. You can have up to 4 intermolecular hydrogen bonds per molecule, and these bonds are very strong because you have a high polarity, and that's what gives water its unique properties. This is a phase diagram of water. This is one of these unique properties. Big range of water, from liquid water from 0 degrees to 100 degrees at 1 bar. And this is where life happens, along this red line at 1 bar, and about above 0 degrees and about 30 degrees, 36 degrees. And this is a zone where water is liquid, and that's essential for life. All the molecules and ion can nicely mix, and you can have these biochemical reactions, and that's life. That's another unique feature of water. It's an ampholyte. One water molecule can give a proton to the other water molecule, and that gives you a hydroxonium ion and a hydroxide ion. And these arrows indicate there's just a little concentration of these ions, and this reaction is on the left side. But still, water has some ionic character, and that's why many ionic compounds are soluble in water, like, for example, normal salt, sodium chloride. And there are also exceptions, like silver chloride and barium sulfate. These are insoluble compounds because they have a high lattice energy. That means the ions fit very nicely together, and the water molecules cannot break them up. Here are some requirements of life. There are 4 main requirements. One is liquid water. you need it both as a solvent and as a reactant. For example, photosynthesis reaction, that's 6 water molecules, 6 H2O plus 6 CO2. Carbon dioxide gives you 1 glucose molecule, and the byproduct 6 oxygen atoms, which is released to air. And you need an energy source, that's typically the sun. There are other chemical energy sources, but the sun is the dominant energy source. And you need basic molecules like CO2, carbon dioxide, ammonia, to form complex molecules, for example, amino acids, then proteins, DNA. And you need minerals. That's ions, iron, magnesium, sodium, potassium, calcium, chloride, iodide. Here are more requirements of life, more essential phenomena that enable life. First is Earth's magnetosphere. It protects the Earth's atmosphere from the charged particles of the sun. This magnetic shield is not perfect. The Earth still loses a little bit of atmosphere to space, but it's insignificant. And another factor is volcanism and plate tectonics. These mechanisms provide essential minerals from inner Earth to the surface, and this is a big spark for life and a big advantage. And one more requirement is the moon's gravity. This is like a big mixer. It mixes all the water masses, and so the molecules and ions can react, and you can have biochemistry, and that also supports life. This is one important requirement for life on land. That's the ozone layer. You can see ozone is also a band molecule, a bit like water. And this diagram shows how this works. Oxygen atoms, O2, absorb UV photons. They get broken up to oxygen atoms. And the atoms react with other O2 molecules and form O3 molecules. And the ozone molecules, O3, can also absorb UV photons. And they are broken up, and you get back O2, oxygen. And this O2 and O3 cycle converts dangerous UV photons into harmless infrared photons. And that protects the life on Earth, on land, because the high energy UV photons would destroy all organic molecules. And the ozone layer prevents that. This is another anomaly of water. It's a density maximum at 4 degrees Celsius. Above 4 degrees Celsius, you have a lower density because of more movement of the water molecules. And below 4 degrees Celsius, you have also a lower density because the water molecules have a more order. And bottom graphics shows the consequences for life in water. This means that a river or a lake will always freeze from the top to the bottom, and that's very essential for life. But in the winter months, when the temperatures drop, it will take quite a while before the water starts to freeze, and that's because of the high heat capacity of water. You can see in this diagram there are several water cycles. There's the water cycle in the atmosphere, and there's another water cycle in the oceans, for example, the Gulf Stream, which transports hot water to, for example, North America and Europe. And both the cycles are driven by temperature differences between the mild zones, climate zones, and the equatorial zones. And because of climate change, these temperature differences are getting lower, and that's why these cycles are weakening, and it could be that the Gulf Stream could totally die, and that would be very bad news for North America and for Europe, for example, for agriculture. And the human body, the water in the human body helps also, the heat capacity of the water helps maintain the temperature of 36.5 degrees in the human body. This is another feature of water. It's a high surface tension. Water strider makes use of that with its long hydrophobic legs, with tiny heads that repel water, and the water stride has also a nice weight distribution, and that helps it to stand on water. There was an incident in the 60s during the Cold War. This was the Polywater. That started. Somebody started a rumor that Russians or the Soviets had made Polywater, and that started a run among scientists. And several people claimed that they had also made Polywater. And another scientist even warned that we should not put Polywater in the environment because it would infect all other water and turn it into Polywater. But there's one problem: Polywater doesn't exist, and the reason for that is water has a high bond energy, and there's no driving force for polymerization. You can see on the top the polymerization of polyethylene and ethylene. This is due to the fact the carbon-carbon double bond has a lower bond energy than two single bonds, carbon single bonds. So the polymerization of ethylene is an exothermic reaction. You need actually cooling to control this reaction. But Polywater does not exist, and there's a lesson to be learned here, and that is don't let crazy propaganda poison your mind. That's very important. But heavy water exists, and this is due to the fact that there are several isotopes of hydrogen. For example, the most common is protium, 99.98%. Then the second is deuterium. It has one proton and a nucleon in the core, and 0.015%. And there are traces of tritium. This is radioactive. It has two neutrons in the nucleus and a half-life of about 12 years. And deuterium, you can neglect the mass of the electron is much lighter than protons and neutrons, so the deuterium is about twice the mass of protium. And you can see it makes a difference in the molar mass, about 10% higher. Also density is 10% higher. D2O has another density maximum at 11.6 degrees Celsius instead of 4.4 degrees Celsius. And the boiling point is 1.5 degrees Celsius higher. And this means the heavier D2O has lower reactions, and you can take advantage of that and for the isolation of D2O from H2O. This is what you need D2O for in the nuclear fission reactor. It has 4 components. You need nuclear fuel rod. It's made. It contains uranium-235, but you can't use mined uranium directly because it has only 0.7% of this isotope. You need a concentration process to increase the concentration to at least 3%. The next component is the control rod. It's made of graphite. It's the most important part of the nuclear reactor because it's the part which can stop the nuclear reaction. That's a neutron absorber. And you need D2O. This has the role of a moderator. This means it converts quick neutrons into slow neutrons, and you need slow neutrons to maintain the nuclear reaction. And the last component is the reactor coolant. It's normal water. And that's a problem because coming years it will be more hotter, and we had already this year near record low levels in rivers of water. So you have not enough water to cool the reactors, and the water is too hot. So so that's why, in my opinion, a nuclear fission reactor has no future. We should end this technology as soon as we can and convert to renewable energies. Here are some stats about H2O. 71% of Earth is covered with H2O. Most of it, 97%, is salt water. and only 3% is freshwater. However, most of the freshwater is also not available because it is trapped in the polar caps or in the glaciers, and rest is in groundwater and rivers. And in the end, only 0.4% of the water is really usable. The human body contains 60% H2O by weight. So the most common element in human body by number of atoms is hydrogen, by weight is oxygen. And if you drink about 2 to 2.5 liter waters a day, then you will be fine. 2.2 billion people have no access to clean water. That's very sad. There was a Greenpeace report which said if we could shut down all coal power plants, we could save water for about 1 billion people. And that shows you what a wasteful technology coal power plants are. They're big CO2 machines. They waste a lot of water, they pollute the air, and they burn a lot of money because you have to pay subsidies, billions of euros and dollars subsidies, and really this technology has no future. Here's an example of one of the products, and it's water need. That's beef. You need 15,415 liters of water for 1 kilogram beef. And in Germany, there's a TV station called Arte. They have great documentaries about the water consumption or general resource consumption of all kinds of products. And that's very unfortunate because this TV station Arte is only in French and German, but not in English. That's very unfortunate in my opinion. And other known products that have a high water consumption are, for example, chocolate or avocado, or also cotton. And right now there are startups. They want to build a mass production of clothes using hemp. And that makes a lot of sense because hemp is known for its low water usage. Here are some new technologies or some modifications of new technologies. For example, desalination. Yes, there has been some progress in recent years with new membranes, new filters in the desalination technique. But it's still very expensive, and you need a lot of energy to make water out of salt water. Drip irrigation is used, for example, in Spain. That's a very efficient use of water. The idea is to release the water as near to the roots as you can, and that minimizes the loss to evaporation. Another technique is vertical farming. Vertical farming makes a lot of sense because it is known for its low water usage. You can produce locally. That's also a big advantage. You don't need all the chemicals to protect the plants because you have a closed system. And this technology is often criticized as too expensive, but I don't think so. You have to do the math right, and it's not just about the money that you pay at the grocery stores for all these products. You have to add the subsidies that you pay with your taxes, and you have to add the compensation for the environmental damages that you also pay with your taxes. And if you add all this money, then you will see it's actually the conventional agriculture that's too expensive. And another technology that's in development is a cultured meat made of cultured cells, and that's also would be a great benefit if we could make this work, and that would save a lot of water, but also land that we could give back to nature, let it regenerate. And that's why all these technologies make a lot of sense, and we should continue to develop them. That was about water in our world. Now about water in other worlds. This was a great surprise for scientists. when they had the first measurements of these two moons, Europa and Enceladus. Europa is a moon of Jupiter. It is a bit smaller than our moon, Earth's moon. And the surprise was that these moons were much warmer than previously expected. And Jupiter and Saturn are far away from the habitable zone of the Sun. But it may be that they have their own habitable zone. And the reason for the higher temperatures is tidal heating. These moons experience gravitational pull from the planet. In Europa's case, it's Jupiter, but also from other moons, and that causes a tidal heating, internal heating, and that is hot enough to produce liquid water in the interior of these moons. And this means you have all requirements for life are met. You have liquid water, you have the minerals, you have basic components like ammonia, carbon dioxide, and you have the energy source. Plus we have ice shield at the surface. The ice shield protects the underneath ocean from the cosmic radiation, and that's why I've made a yellow check here. These moons could be potential places for life. The second moon is a moon Enceladus. This is a tiny moon, just a 504 kilometer diameter, and this moon also experiences gravitational pull, and it's a very beautiful moon. And you can see in the southern hemisphere there are these green stripes. They are called tiger stripes. These are geysers, and whenever Enceladus is further away from Saturn, the gravitational pull loosens a bit, and this geysers emit ice particles, and this moon can also be a potential place for life. This is the system Kepler 442. It's a super Earth system. It's located 1206 light years away from the Sun. The star is a K star. This means it's about 15% lighter than the Sun, as also less luminous. And the planet Kepler 442b is at about 0.41 AU distance from its star. 1 AU is about 150 million kilometers. It's the distance between Earth and Sun. So 0.41 AU is about 60 million kilometers. And that was a great scientific success of the Kepler mission. It has discovered a new class of planets. They have the size between terrestrial planets like Earth and ice giants like Neptune, Uranus, and these called super Earth. And this planet could have twice the mass of Earth, and average temperature is calculated to be minus 40 degrees Celsius, but of course it depends on the atmosphere of this planet. And we will soon learn more about the properties of these planets. It could be that there's a big diversity in this group of planets. And the James Webb Space Telescope will very soon deliver spectroscopical data of their atmospheres. And we live in a great time for science, and a big fan of NASA. This is a very interesting target for the James Webb Space Telescope. The TRAPPIST-1 system is just in distance of about 40 light years. Its star is M-star, red dwarf. It's the tiniest star. It's just 9%. It has just 9% of the mass of the Sun. Typical luminosity for about 1% of the Sun's luminosity. And you can see there are seven about Earth-sized planets in this system. Most interesting seems to be the planet E, which is right in the habitable zone. But also the D, F, and G, they all could be habitable. It depends on various factors like the composition of the atmosphere. And we will very soon learn more about these planets. These are, of course, just computer renders. And this is a very interesting system. It may be that several of these planets are habitable, but it could also be that none of them are habitable. And more and more information will be available in the near future. And this picture shows you the power of the James Webb Space Telescope. It has measured the atmosphere of a gas giant that is 1,150 light years away. That's WASP 96b. It's a hot Jupiter. It's very close to its star, at just about 0.0545 AU. It's hotter than, it's about 1000 degrees Celsius hot. It has half of Jupiter's mass. And the spectrum shows several peaks, and they come from the molecule water. All molecules that have at least 3 atoms are infrared active. That's because of the selection rule. I will explain this in my next video. And yeah, this shows gives you a glimpse of the possibilities of the new James Webb Space Telescope. And yeah, this is a great success. My next video will be about CO2. It's a molecule that's always in the news. And I will explain its properties, its effect on the climate. And a project of in Germany is called Energiewende. That's the transition to renewable energies. That was today's video about water. Thank you for watching. Have a nice day. Bye-bye.